Hello, my name is Mark King, and you are listening to the seminar series that I sponsor in my role as Atlantic Canada representative of the International Association of Hydrogeologists, the IAH. In this capacity, we solicit seminar presentations from speakers all over the world. The general topic is groundwater and hydrogeology, but within that field, the talks can vary over a wide range, from water supply to geochemistry to remediation to the fate and transport of groundwater contaminants and beyond. And at times we may also stray outside the bounds of hydrogeology when a particularly interesting technical topic or speaker comes our way. Welcome to our seminar series. My guest today is Steve Shikaze. Steve is a senior hydrogeological engineer with Matrix Solutions Incorporated in their Ontario office located near Waterloo. He graduated from the University of Waterloo with an undergraduate degree in geological engineering and a master's in earth sciences. Steve has over 20 years of groundwater modeling experience in academia, research, and consulting. Steve's presentation today is entitled Groundwater Modeling, Case Studies in Consulting. In it, he presents a consultant's perspective on modeling through two case studies. The first concerns a groundwater flow model constructed for a municipal government. The second is a groundwater flow and transport model constructed to evaluate a lithium brine resource in South America. And I believe I had the pleasure of working with Steve on that one.
Hi, Steve. How are you?
Hi, Mark. I'm doing great, thanks.
You having a good summer in Ontario?
Yeah, it's been a cooler summer than usual with a little bit more rain, but after the winter we had, it's been nice to finally be out in shorts.
Excellent. Listen, I'm really looking forward to this talk that you're going to give to us today, this presentation. I understand that you originally put this together for a grad course at the University of Guelph.
Yeah, I was invited back in the spring by Dr. Jenna Levison, who's a prof in engineering at the University of Guelph, and she teaches a grad course in groundwater modeling, an introduction to groundwater modeling, and she invited me to give a talk to her students to give a consultant's perspective on groundwater modeling and how models are used in industry. So that leads into my talk, and I'll be presenting the same talk here for Mark's IAH session, and I'll be presenting a couple of case studies.
Well, great. You carry on, Steve.
Okay. Thanks, Mark. So just for an outline, I'm going to just present a very brief background into the kind of work that we do, which will lead into the case studies. The first case study involves groundwater flow in a southern Ontario site where we did a water quantity risk assessment. And the second example involves running both groundwater flow and solute transport models for a lithium resource in South America. Just a brief background of what Matrix Solutions is. It's an environment and engineering consulting company of about 600 people with offices across Canada. I work out of an Ontario office that focuses on quantitative hydrogeology and hydrology with an emphasis on modeling. Just to give you a bit of background about numerical modeling, what we try and do with models is simulate all or various parts of the water balance. In a surface water model, we deal with physical processes that occur at or near the ground surface, such as precipitation, evaporation, transpiration, surface runoff, and then processes at surface water bodies. In a groundwater model, we're looking at the subsurface, where we consider deeper processes such as recharge at the water table, pumping, groundwater flow, and then discharge to surface water bodies or to ground surface. In integrated modeling, we combine both surface water and groundwater modeling. And for the case studies that I'm presenting today, I'll be looking at two examples of groundwater modeling specifically. So on to the first case study. The first case study focuses on a three-dimensional groundwater flow model for a water quantity risk assessment. And in this case, the client was the Upper Thames River Conservation Authority, located in southwestern Ontario, covering the counties of Perth and Oxford, and I'll show a map of that shortly. But give you a bit of background as to why we did this project. Source water protection in the province of Ontario is the result of the Walkerton tragedy in the year 2000, where 7 people died because of E. coli in the municipal drinking water system. As a result of this tragedy, an inquiry was held, and the result was the O'Connor report, which focused on drinking water from both a water quality and a quantity perspective. This in turn led to the Ontario Clean Water Drinking Act in 2006, which protects municipal drinking water sources in Ontario. And for this case study, we'll be focusing on just the water quantity issues. So in order to assess potential water quantity issues, the sustainability of municipal water systems must be evaluated. This includes examining potential quantity issues under current and planned demands. And the approach from the MOE is a tiered approach from simple screening tools to a detailed water budget or numerical modeling tools. And that's shown in a little bit more detail, where we go from simple conceptual water budgets at the watershed scale, moving up to through this tiered approach, Tier 1, Tier 2, and Tier 3, where Tier 3 focuses on the local areas and generally consists of 3-dimensional groundwater flow models. So we're increasing the certainty, or decreasing uncertainty, and increasing the model complexity as we move through this tiered system. The case I'm studying, or the case that we studied that I'm presenting today, involves a Tier 3 assessment. So the focus or goal of a Tier 3 risk assessment is shown here. We use numerical models to assess the ability of a municipal water supply system to meet future water demands under the following scenarios. The first scenario, we increase demand based on population growth and assumed per capita water use. In the second scenario, along with that increase in population, there's an accompanying projected land use change. And in the third scenario, we look at drought conditions. By examining historic climate data, we can look at when precipitation was lowest and use that to over a extended drought period. And again, we use our numerical models to do this assessment. And as I mentioned, it's the Upper Thames watershed, and this map shows the outline of the watershed, shown as a dark line. Just to orient you, Kitchener-Waterloo is outside of the domain, up here in the northeast. The City of London, Ontario is here in the southwest of the domain. That means Toronto is further east, or further to the right here by about an hour from Waterloo. Specifically, the areas of interest within this watershed are 6 systems or 6 communities, and those are Stratford, small town of St. Paul's with 1 well, St. Mary's here in the north. This is Perth County. And in the south, there's the communities of Woodstock, Beachville, again, a small community with 1 well, and then Ingersoll down here. So as with many model projects, there's a phased approach to building the models. The first phase being assembling and gathering all the background data, including previous consulting reports, government reports, any climate data such as precipitation, streamflow data, land use maps, as well as official planning maps from the municipal governments, borehole logs, pumping tests, and any other geologic or hydrogeologic data, municipal well pumping data from the municipalities as well, and any other monitoring data to get transient water levels over time. Phase 2 in the creation of these models is to come up with a geological characterization. And because we're dealing with 3-dimensional models, we need to come up with a 3D geologic characterization as well. This figure here shows a vertically exaggerated slice of our 3D model, and you can see how we've come up with geologic layers in a 3-dimensional context. So the phase three of the modeling process included the development and calibration of the numerical models. And for this project, we first used a surface water model to estimate recharge that would in turn be used for a groundwater model. And in this case, the surface water model that we used was called GAUSR, and that stands for Guelph All-Weather Sequential Events Runoff Model. And once we were able to use climate data and surface topography and so on to estimate groundwater recharge, we calibrated the stream flow, and we used that recharge into the groundwater models. So once the models were built, they were then calibrated by fitting model results with observed data. And once we were satisfied with the calibration, we were able to use the models to estimate water levels at the municipal pumping wells for these various scenarios that I introduced previously. So I'll just talk about that in a little bit more detail. For this particular project, as I mentioned, there were 6 communities. And for those 6 communities, we ended up building 3 models. So for the Woodstock, Ingersoll, and Beachville model, or area in Oxford in the south, we built a new model using fee flow. For Stratford and St. Paul's, we built a mod flow model, and for St. Mary's, we built a separate mod flow model. And the reason for these separate mod flow models were that there was existing work that was done that we wanted to build upon rather than starting from scratch. So for this talk, I'll be focusing on item 1 on this list, the fee flow model that we developed for the 3 communities in Oxford. So this map shows the southern area of the Upper Thames watershed. The model domain is shown as a purple boundary. The Thames River is shown here as a light blue line, flowing from the northeast towards the southwest, towards London, which is in this direction. The communities of Woodstock, Beachville, and Ingersoll along the river. And you can also see this blue line here, which represents the southeast boundary of the watershed. And we extended the model beyond the watershed because capture zones within Woodstock might go outside of that watershed boundary. This figure shows a regional cross-section through the 3 communities from west or southwest in Ingersoll through Beachville and to the northeast in Woodstock. And you can see, in this case, overburden is colored as one single color in this particular figure. And you can also see the sedimentary bedrock units with their formation names shown as oranges and yellows and greens below. These bedrock units are of significance for many of the municipal wells in this area because they're very productive aquifers. As we look in a little well through Woodstock, this particular cross-section, you can see that in this now that we've been able to create a three-dimensional geologic model, we've actually divided the overburden, which was a single color in the previous figure, into several different layers to represent the overburden in a more detailed manner. The bedrock units in the Woodstock area are shown here, and you can see that there's a number of wells shown along this cross-section. This is a cross-section through Woodstock from west to east, and a number of the wells go down into bedrock, but most of the wells are in the overburden. In the Woodstock area, the overburden is very thick. Some of the municipal wells draw water from the overburden, and some of the wells draw water from the bedrock. Look at a similar section through Ingersoll, which is the community to the west. We see the overburden is much thinner, still characterized by a number of layers, but most of the wells in this area are much deeper, and all of the municipal wells in Ingersoll, in fact, draw water from the bedrock. So with all that information, we were able to build a mesh in fee flow, and fee flow uses triangular elements. The 3D geologic characterization was translated to create the 3D fee flow model, and the mesh is shown here. So on the left, municipal wells are shown in green, and other private wells are shown in orange. The streams, with the main one being the Thames River, are shown as blue lines. A close-up of this mesh is shown for the south part of the Woodstock area here, and you can see how the mesh is refined around the wells, and the mesh is also refined along surface water streams and rivers. And this was done because hydraulic gradients are expected to be the highest in these areas, and we wanted to be able to capture those high gradients, so we had to put in finer or smaller cell sizes. The resulting mesh covers an area of about 780 square kilometers. There's 16 model layers. That includes both overburden and bedrock. About 2 million mesh nodes and nearly 4 million triangular or prismatic finite elements. This slide shows a 3D view of the model domain, and you can see it's vertically exaggerated, but in the front you can see there's 16 model layers, and you can also see the topography reflected on the top surface with the rivers incised into the digital elevation model. For the parameterization of the fee flow model, we assign properties such as hydraulic connectivity and storage to each finite element in each layer. When constructing numerical models, typically each layer is assigned a unique value of K, hydraulic connectivity, for example, with some refinement or K zones within each layer. The values assigned to these K zones and layers are then adjusted during the calibration process. For this particular model, we used a method called the pilot point method. And I'm not going to get into a lot of detail here, but pilot points are locations that guide the distribution of, again, hydraulic connectivity, for example, throughout the model domain. So within each layer, hydraulic connectivity is spatially variable within a specified range. And that's shown a little bit more. So in our case, the resulting hydraulic connectivity is shown in the bottom figure. And you can see for each layer, there's a fairly smooth transition in the variable hydraulic connectivity for each layer. Typically, when we're dealing with hydraulic connectivity zones, we have sharp changes in properties within a given layer. And that's what's typically done, or it has been in the past. And it can result in some numerical problems because we're looking at zones of adjacent zones of highly contrasting property values. For model calibration, we focused on both steady state and transient groundwater flow. For steady state, we use the Water Well Information, or WWIS system, which is the MOE well database, for wells from 1970 to present. In addition, we use data provided by the University of Waterloo for research they've been doing from a study near Woodstock. And we also calibrated to stream gauges at 2 creeks within the model domain. For transient calibration, we calibrated to transient water levels at the municipal wells for the period from the year 2000 to present to get the most recent data available. For calibration targets, again, here's our model domain. The black dots represent the WWIS wells from 1970 to present. There's other test wells in the area shown here, mostly in the Woodstock area. And there's also the municipal pumping wells, which are hard to see, but they're larger green dots near the communities. There's also 2 stream gauges, as I mentioned, one the south end of Woodstock here, and then one southwest of Ingersoll. For the approach, we first set initial values as well as min and max ranges for the control points or pilot points within each model layer. These values were selected on the basis of available data. The next step involved using parameter estimation or PEST software to optimize the parameters for both steady state and transient simulations, or calibration, I mean. The results of the steady state calibration are shown here, and these figures show scatter plots of simulated on the y-axis versus observed on the x-axis head measurements for both the overburden and the bedrock. An ideal fit is a 45-degree line, and there's 5-meter error bars shown on each figure. So what this shows is that the trend is fairly close to the 45-degree line, and the mean error was about 2 meters, and the normalized root mean square error was less than 5%. So we're pretty happy with the way we're able to calibrate this model for steady state. The resulting equipotentials in the overburden for the steady state model are shown here. Water table contours generally mimic the ground surface topography, and flow tends to converge towards the Thames River, which is a regional discharge area. The highest gradients tend to occur near the river and near the municipal pumping wells, particularly in this area here where the Woodstock overburden wells exist around where the Woodstock moraine is present. Lowest gradients occur in the uplands at distances away from the river. This figure shows the same equipotentials but in bedrock, and water levels tend to be similar in trends to the overburden with a slightly more subdued expression. And as we saw in the previous slide, water contours tend to converge towards the river. One last on the steady state calibration, because the focus of this project was on the municipal wells, we wanted to make sure that the model was representing the water levels at these wells. So this figure shows the range, shown as blue bars, in water levels at each municipal well, as well as the steady state water level predicted by the numerical models, shown as red lines. So ideally, we'd want every red line to fall within these blue bars, and we've done a good job in all of them except for two wells here in Ingersoll. And these two wells, well 7 and well 10 for Ingersoll, the reason that these don't match was the ranges that we looked at for the water levels represent lower water levels, and these wells have not fully recovered. So the historic declines have not been represented in these models. So the steady state pumping rates we actually used are very low, and it's not reflected in the field data. For trend calibration, we tried to fit transient water levels at the municipal wells in the model to observe data. This figure shows the results at two municipal wells, one in Woodstock and one in Ingersoll. The blue dots in each figure represent the observed water levels, and the orange lines represent model results. So you can see we've been able to match the trends reasonably well, the transient trends in both of these, and that gave us the confidence that our model was calibrated. Once we were,
would you mind going back to that previous slide?
Yep.
So what is it in the model that is causing these fluctuations in the orange line?
So there's changes in the transient model. There's changes in pumping rates, monthly changes in pumping rates. There's also transient recharge. That's so the model is responding to those two transient inputs.
Okay, thanks.
So once we have this calibrated model, we could use it for the water quantity risk assessment for things such as wellhead protection areas or WAPAs, as well as to simulate scenarios such as increases in pumping and drought conditions that I introduced previously. And then we were able to examine changes in drawdown at these wells in response to these scenarios. So the first result is shown here. With the steady state model, we were able to create the wellhead protection areas, or WAPAs. In this case, the 2-meter contour is shown as the outermost contour here, the lightest brown. And this has been delineated as the drawdown cone of the municipal wells, or well fields, when pumping is at current rates compared to the non-pumping condition. For the water quantity risk assessment, we needed to see if water levels at the municipal wells fell below what we've defined to be the safe water levels under the various scenarios. An example is shown on this slide for a single well. So the well is shown here on the left, with its screened interval shown in gray here at the bottom portion of the well. The pump elevation shown here. The current water level, which is up here, higher in the well. And then this blue bar represents what we've defined as the safe additional drawdown. So the water level in this well can draw down anywhere within here, and we still consider it to be safe with no water quantity issues. On the chart on the right, we see the same values. With additional information such as the average annual pumping rate at that well. The monthly pumping rates are the fluctuations shown as the green plus symbols. We have our safe water level, based on the screen and the pump elevation and so on. We come up with a safe water level. The average water level in that well over the study period, or period of interest, from 2008 to 2013. And we have the dots represent observed groundwater elevation at those wells. So the blue line is an average of those purple dots. Also, so in this case, the orange line is what we're interested in, and the orange line represents the minimum water level in that well for the various scenarios that we ran. And if you recall, we ran the drought scenario, an increase in pumping based on projected population growth, and so on. And with the various scenarios, each one resulted in a model run that gave us a water level at this well. And of all those scenarios, the lowest water level was the orange line. So what we're interested in looking at in this figure is, under all those scenarios, does that orange line drop close to or below the red line, or the safe water level? And if it did, then we could say there was a risk of a water quantity issue at that well. In this particular well, we still have about 8 meters of safe additional drawdown. So there's not a water quantity issue at this well based on our modeling analysis. And that takes us to case study 2. In this case, the client was in the mining industry. Specifically, the resource is lithium, which is used for batteries and electric cars and mobile devices and so on. And the client was Lithium Americas Corporation, or LAC, and the site is in Argentina, and it's a salt lake, or what's referred to as a salar. Just for some background, in the central Andes in South America, the Andes, Central Andes is a north-south trending mountain range with elevations exceeding 4,000 meters. And there's a number of salt lakes in the area, which are basically these flat, arid areas where the groundwater in these salars, or salt lakes, are brines with very high concentrations of total dissolved solids. And these brines, the brines in these salars, are estimated to contain somewhere around 70% of the global lithium brine resources. And LAC has a site shown here in red in northwestern Argentina, in Argentina, near the Chilean border to the east and the Bolivia to the north. So this area includes 2 salars, the Cochari and the Olaroz salar, which have been identified as potential sources of lithium. And for this project, we needed to quantify the resource and the reserve of lithium that exists at this particular salar. So as we zoom in on the site, this figure shows a close-up of the Cochari salar here in the south and the Olaroz salar in the north. The LAC land claims are outlined by dark lines. There's a part out here, but they're mainly interested in this central area. The model domain that we set up is shown in yellow here. To introduce this project a little more, this slide shows some key terminology that I'll define. So first, to be a publicly traded company on the Toronto Stock Exchange, there's a need to provide documentation on estimates of the resource, which is how much of the mineral is in the ground, and the reserve, which is how much can actually physically be extracted. So for lithium in brines, the resource can be estimated by trying to get an understanding of the volume of the mineral in the system. In this case, lithium, multiplying that by the porosity, because it's a brine that fills the pores, and multiplying by the concentration of the resource in the brine. So it's lithologic volume times the porosity times the concentration gives us an estimate of the resource. For the reserve estimate, we used a 3-dimensional numerical model to represent the system, and this required estimates of porosity, transmissivity, and storage, as well as an initial concentration distribution that came from the resource analysis. The conceptual model for this system is shown here. The salt lake in the center here is bounded on both sides by mountain ranges, and on the bottom by a lower permeability basement rock. Precipitation occurs primarily in the mountains, and fresh water recharges from this area towards the center of the salar. Water leaves the system by evaporation along the top of the salar. So we have this system where fresh water enters from the sides and stays near the ground surface and gets evaporated, concentrating the brines or salts that are in the salar. So just for review, the resource comes from a data analysis, field work, and interpolation, whereas the reserve is estimated using the numerical model. We're looking at fresh water with a density of about 1,000 kilograms per cubic meter coming in from the margins. Lithium concentrations are fairly low. Within the salar itself, we're looking at brines that have a total dissolved solid concentration of about 350,000 milligrams per liter and a concentration of lithium greater than 600 milligrams per liter. So the first step was to come up with a resource estimate. And to estimate the lithium resource, we developed a three-dimensional geologic model, and a sample cross-section of this model is presented here. The underlying salar sedimentology is a complex pancake of the main elements, all the way down to the basement rock. And in this case, we came up with 24 layers that are laterally continuous. Initial hydrogeologic properties then were assigned to each of these layers based on field investigations such as pumping tests, borehole logs, lab analyses, and so on. A key feature of this conceptual model is this laterally significant mud complex shown here near the surface in blue. And this underlies the alluvial fan complex. And groundwater above this mud tends to be very low in total dissolved solids and in lithium. And it reflects a shallow flow system that I talked about, where rainfall comes from the mountains and recharges in the top of the salar. Beneath these mud complexes, there's confined sediments with lithium concentrations of 500 or 600 milligrams per liter and TDS values as high as 350,000 milligrams per liter, or about 10 times that of seawater. These dense brines then are the target for the proposed mine development. But it represents the stratigraphic brine model, and with all the available data, based on our conceptual understanding, we came up with a three-dimensional model. As the video rotates around, you can see very that shows. Towards the end of this animation, you'll see a brightly colored lens. The liquidated. So field investigations were carried out to obtain all the data to estimate the resource of lithium. And from this information, we created the 3D geologic model that I showed previously. And the next step was to estimate the distribution of lithium that I showed, but not really talked too much about. And this gives us sort of you can think of it as a 3D lithium plume, naturally occurring lithium plume within the salar. So using the 3D analysis, field data, we were able to come up with a lithium distribution where higher lithium occurs at depth because of the density of the brine. And we were able to come up with an estimate of about 1.2 million tons of lithium within this study area. And that represents our resource. That takes us on to the estimate of the reserve. And as we set up a 3D numerical model using fee flow. And this fee flow model was created based on the 3D geologic model shown previously. And the mesh is shown here on the left. The 3D mesh is shown here on the left with a close-up as shown on the right. And as we saw in the previous case study, the model has been refined in areas of the wells. And we also use a finer mesh in the area of the salar shown in this area, as opposed to the coarser mesh outside our main areas of interest. For parameterization, as we saw in the first case study, we assign parameters to the various model layers. And for this model, we used that K-zone method that I touched upon previously. So we didn't use pilot points because of time and budget constraints. So we assign K-zones within each layer, and you can see, as I mentioned previously, in this case, we actually do have some sharper interfaces between K-zones within certain layers. Again, just to refresh your memory, there's 24 layers here, mostly sand, representing sand, salt, and mud units. For boundary conditions, we assigned, around the perimeter of the domain, we assigned recharge fluxes based on water budgeting that was done. And along the top of the model, we assigned evaporation within the center of the salar, where, as I mentioned, in the conceptual model, water is continually being burned off and evaporated because of the arid climate in this area. And recharge was also assigned in areas where recharge was estimated based on water budget modeling. For the initial conditions, we used the lithium distribution that we determined when we estimated the resource that I showed previously. And that's shown here on two cross-sections, north-south and east-west cross-section. And you can see higher concentrations of lithium that are assumed to be occurring at depth. For model calibration, we were able to compare the water levels at several wells over the course of a 30-day pumping test, and two of the wells are shown here, with modeled results shown in red and observed results shown in blue. And you can see we were able to come up with a reasonable calibration, which gave us confidence that our model was representing what we saw in the field. Once we were satisfied with the calibration of the model, we were able to examine the response of the system to a network of pumping wells shown here as red and white dots. And the network was set up in the model to try to optimize the extraction of lithium across the site. So we wanted to be able to withdraw lithium almost as exclusively as we could within the claim boundaries, and also not have a lot of overlap between where each well was drawing its water. So this slide shows the results, and on the graph on the left shows the cumulative lithium pumped over the 40-year period, or assumed period of the mine. And it also shows the rate of lithium production per year for each of the 40-year simulation period. The short video on the right shows the evolution of particle track at the extraction wells. And by examining these particle tracks, we were able to examine if the pumped brine was coming from off-site, and we could also ensure that the pumping from the well network covered the majority of the claim areas. So again, this short animation hopefully shows up, shows the capture zones at 5-year intervals up to 40 years.
So Steve, I guess it's probably worth mentioning that those growing capture zones around the wells were actually the constraint for the reserve. So when those grew so that they were starting to capture product from outside of the claim boundaries, then that particular well would be shut down, and ultimately all the wells would be shut down when too much production was taking place from outside the reserve. Is that correct?
Yeah. So the pumping wells were not pumped at the same continuous rate for the entire 40-year simulation, as Mark mentioned, and we worked with Mark on this project actually, and some of the wells get shut off earlier as their capture zone starts to reach the boundary. Other wells start with lower pumping rates and get turned on over the course of that. So there's a little bit of a trial and error to get to what we consider our solution for the reserve. So in summary, for this study, we were able to develop first a 3D geologic model to support the estimate of the resource. And then we developed a 3D groundwater flow model and flow and transport model to support the reserve estimate. The model was also used to improve our understanding of recharge and evaporation and the water budget for the system, as well as provide an initial design for the well network to meet the lithium extraction requirements. So that takes me to the end, and if anybody has any further questions, feel free to email me at the email listed below. And Mark, if you have any other questions, I'd be happy to try to answer them.
Oh, that's great, Steve, and thanks for indicating that you'd be receptive to some follow-up questions by email. That's really helpful. Just to step back to the municipal modeling that you did, you mentioned that at a couple of the sites there was already pre-existing mod flow models, but you folks chose to actually develop, and for one of the sites that I guess didn't have a model already, you chose to use fee flow. Can you talk about, I guess, the preference between fee flow and mod flow, and maybe just briefly the reasons for the preferences, and also, I guess, if there is a preference, sort of a three-part question, if there is a preference, can you talk about how universally it's held amongst people using these models for these municipal sites? Like, is fee flow now, for instance, the universally preferred solution for these type of modeling projects?
I think, I guess to answer that question, first I'll talk about my experience and our experience within our office. When given a choice, we'll generally pick fee flow if we're starting from scratch. And the reasons for that include, because it uses triangular finite elements, there's a lot more flexibility when designing a mesh. So if we want to refine and use very small element sizes around wells and around streams, for example, we can do that without affecting any areas beyond that specific area of refinement. So it allows a lot more flexibility in terms of the mesh. So that's generally our approach is to use fee flow. As for universal acceptance, I guess my experience is people will use either, and whatever advantages fee flow has, they'll accept that if they use mod flow, and they'll try and make the best out of their mod flow, and a lot of it depends on their experience. So fee flow is generally thought of as a newer tool. So people that have been using mod flow and the interfaces that go along with mod flow, such as visual mod flow or groundwater vistas, users that are familiar with those tools tend to stick with them. That's my experience anyways. So as far as something that's universally accepted, I think both are. And because both of them are accepted, people that are making decisions, in this case municipal governments, if you make a case for using either one, they're really not going to question it. I think some issues with that come up when you try to introduce something that they've never heard of before. Sometimes a research-oriented code or something they've never heard of, they tend to be a little bit more reluctant. So in our experience, fee flow and mod flow are pretty accepted in that sense.
Right. Okay. And now fast forwarding to the lithium project, after we have a calibrated model, flow and transport model in the case of this project, it seems it comes down to the different constraints that get placed on the model to actually define, okay, to pump any further is not practical for either for chemical reasons or for legal reasons, property rights, etc., or hydraulic reasons. Can you talk about the different constraints that we used?
I guess I mean you summed it up fairly well there. When we're looking at the capture zones and that capture zone video, we wanted to make sure that we didn't want to draw water from outside of the claim area. So we had to pay attention to where water was being drawn from over the course of that simulation. The other thing was we wanted to make sure we were still withdrawing lithium at a rate that was still economically feasible. So if concentrations dropped off after the first 10 or 15 years, no matter how much water we could still pull out from within the claim, if concentrations dropped off, then it wouldn't make sense wouldn't make economic sense to continue to remove it. So we were looking at both concentration constraints and the flow constraints.
So that particular well or wells would be shut down, and maybe others would be either installed or others would be pumped harder.
Yeah, correct.
And then the last thing is for the well drawdown considerations. Right.
Yeah, drawdown in the wells was examined. That's a good. I forgot to mention that. So if the water level in a particular well got drawn down to too low, and I can't remember what the actual constraint was there, but we would stop pumping or reduce pumping at that well.
Yeah, it seems, Steve, on a lot of these lithium sites, especially where there's maybe competitors located on neighboring claims, it seems like one of the big issues that's going to come out in the future is how to protect each claim from mineralization being drawn across the claim boundaries. Can you just speak to that a little bit? How that might be evaluated in the years to come as some of these issues probably start to crop up?
I think that's an interesting point, and I don't know if anybody's really thinking about that, because if there's adjacent claims, conceivably each mining company would have its own model or tools to evaluate how much they think they can remove, or what pumping rates they can use, or what well configurations they can use, and so on. And because of all the uncertainty that goes into these models, two separate models in the same area will likely produce slightly different results, or very different results. So one company might be saying, well, I can pump right here very close to the boundary, and I'm not going to withdraw any of your resource. But the other company might say, well, my model shows that you have to move your well a kilometer away and pump a lot less because you're already drawing my resource. So how that gets resolved is anybody's guess at this point. I think what we can do is make our best guess with the best available tools that we have. How it gets sorted out through the mining industry, I guess, is still remains to be seen.
Steve, thanks a lot for this presentation. It was extremely interesting. Really appreciate your time that you took to put it together and also to present it to us. And I look forward to seeing you again soon.
Thanks again, Mark. Thanks for the opportunity.
You're welcome. We'll talk to you soon.
Bye.